We live? We're live. Okay, so this is like problem 10 or 11.
Are you recording?
I am recording. Do I have sound and video?
Oh, okay, this
Sound
one's
and video. All right. So 10 or 11 toggle back and forth between either inverse tangent or inverse sine or inverse
Both of mine have
cosine.
square roots and 11.
So I would rewrite that instead of tan to the -1, which is tan inverse, I would call it arctan. So I'm just going to rewrite that because that makes me happy. -1 to 1 of twice the arctan of x over 1 plus x squared dx. So there's a hidden bonus in this problem here. What's the derivative of arctan? 0.
1
over 1 plus x squared.
Let me see.
Whatever 1 plus x squared.
Arctan is symmetric about the origin, yeah. 1 over x squared is not symmetric about the origin. It's symmetric about the x-axis. When we put them together, we get a function that's symmetric about the origin. Yeah, I think the answer is 0 here.
And they come
Just look at the graph.
they
What about
squared over
cos-
16.
cotangent?
But I could be wrong. I'm just doing that in my head, so it doesn't count.
I'm gonna try 0.
So I'm going to do a substitution.
Would we be able to use that as our
Dang it.
explanation on the test if this problem came up?
You have to
Graph
be able to justify
I
it.
used-
Yeah,
I did
it's
it in my head.
symmetrical at the origin,
So-
since the two is like.
So if you wanted to say that this was an odd symmetric function, and you would have to prove that f of negative x equals negative f of x, which isn't that hard. We could try it here and see what happens, which is not trivial, but we'll give it a shot. No, I don't want to do it that way. You can do it that way on your own. I want to try another trick first. That popped in my head. I think this is odd symmetric, which means the answer should be 0. Let's see, let's delete that. Delete, there we go. So I'm going to do a U-substitution because I see the derivative of the arctangent on the same integrand. So what is the derivative? Let's see. If U equals the arctan of x, what is du? 1 over 1 plus x squared. Hey, I have a 1 over 1 plus x squared up there. Right?
Yeah.
Yeah, there's a 1 plus 2 with the 1 plus x squared is in the denominator. Yeah.
Oh.
Okay. So up here, what do I have?
So weird.
I have my du is right there, and u is right there. So this substitution, if I pull that 2 out, blue. Other problems today. I must not be tracking right. I get the integral, ignore the bounds for a minute, of 2 times u du. If I wanted to change the bounds, then I'd have to evaluate this thing from -1 to 1. So usually I make a table when I do that, x versus u. If x is -1, what's the arctan of -1? That means what angle goes with the tangent of -1?
Great question.
Tangent is sine over cosine. So what angle has a slope of -1? Okay, let's say
3
what
pi over
angle, what is it?
Wait, -1.
What angle has a slope of 1?
Okay, all students take classes.
What angle has a slope of 1?
All, what?
X.
45. 30.
What is it?
Pi.
45 degrees or pi over 4. Yeah. You have to use radians. Yeah, there's a clock with pi stuff on it up there. You can look at the clock. Silo just realized something. Oh, man.
Wait, if I said a 90-degree angle.
Not 90-degree angle, that would be an infinite slope, or no slope. So pi over 4, oh, sorry, negative pi over 4 goes with -1. Pi over 4 goes with 1. So if I just stick with u's and I don't reverse substitute, then I'm integrating from -pi over 4 to 4.
Do we have to find that? Like, are we gonna have to, or can we just leave it -1 over 1, or we can't do that?
I'll show you the alternative to this in a second.
Okay.
But bottom line is, these numbers up here from -1 and 1, those are x values.
Yeah.
These are now U values. So you have to decide whether you want to stick with the old boundaries or the new ones.
So do we have
I'll
to
show-
sub, do we have,
Just wait. So antiderivative here is what?
U squared.
Just U squared over 2 times 2 is just U squared. And because I already reevaluated the boundaries, I don't have to switch back. I can just say, okay, go from pi over 4 to negative pi over 4. I said that backwards, but I wrote it right. So this is going to give me pi over 4 squared minus parentheses negative pi over 4 squared, which equals
0.
0. Which means it must have been an odd symmetric function, which we could have run that test on it. I'm going to do it a slightly different way. Pacify Ms. Miller.
So arc secant instead of 1 over 1 plus x squared, value of x times.
Wouldn't it be 2?
Hang on. What's that?
Wouldn't it be 2 pi over 4?
No,
Squared?
when you square a negative number, it's positive.
Oh.
So I'm subtracting a number from its positive self, which is definitely 0. Yeah. So you got to use parentheses. Be careful with your signs. All right. So slightly different version of this is if I don't change the boundaries. Okay. So if I leave the boundaries as x goes from negative 1 to 1, and I have 2u du here, then after I say this is u squared, I got to put the x stuff back in to use these boundaries. I can't plug in negative 1 and 1 right now. What is u equal to?
Arctan.
Arctan. So that means now I have the arctan of x squared, and now I can plug in my negative 1 and 1. So then I have to say, okay, what is the arctan of 1 squared minus what is the arctan of negative 1 squared? Okay, can somebody help me out? What's the arctangent of 1? In other words, what angle goes with a slope of 1?
Pi over 4.
Pi over 4. So that means here I have pi over 4 squared. What angle goes with a slope of negative 1?
negative pi over?
Negative pi over 4 squared, which equals
0.
0. Again, yeah, same thing as before.
So we're gonna have.
But at one point or another, you got to deal with the arctangent of 1 and negative 1. Whether you do it later or whether you do it earlier is up to you. There's 2 different ways to deal with substitution in definite integrals. Okay. So I asked a question a couple of times here, and I just want to clarify. When I look at something like the arctan of 1, I ask the question to myself, what angle goes with a slope of 1? Does anybody not get why the hell I said that?
They just do it.
Okay, thank you for saying you don't get it. So arc functions spit out angles. That's what they do. Reversing this means the tangent of some angle, I don't know what, equals 1. Tangent on a triangle is opposite over adjacent, right? Okay. Opposite over adjacent is the slope of that line, right? Rise over run. So tangent connects the slope of a line to its corresponding angle with the x-axis. That's what tangent does. So whenever I see something like arctangent, I'm thinking geometry, I'm thinking angles and slopes. So that's where I came up with that idea. How do I evaluate that? And I just happened to memorize those facts back from basic trig. I got a leg up on you guys because I've taught trig many, many, many times, so it's burned in my memory pretty good. So often I have to draw myself a picture. You know, rise over run is 1 and 1. What angle is that? Pi over 4, 45 degrees, yeah. So this is what's going through my brain. Sometimes I have to write it down to clarify to myself that value. Sometimes I'm going to whip out my calculator to check. But what happens in the calculator if I plug in arctangent of 1? Is it going to tell me pi over 4?
No.
No, it's going to tell me point whatever, blah, blah, blah. That number is a decimal.
So you could put it in as a decimal.
You could, but sometimes you need exact answers. So we want to go for exact answers whenever possible. If the problem said I need exact answers here and you gave me point blah 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 blah
Can you
blah.
do sine? I think I know what it is, but
All right, so there's a similar sign problem to this one. Integral, maybe it was this, -1 to 1 of the arc sine. And I can't remember, was there a 2 in front of
I
it?
think there was a 2.
There was,
Yeah.
over the square root of 1 minus x squared dx. Is that the problem?
I think so.
Yeah, so I think 10 and 11 bounce back and forth between this version or the other one. Did you say you got an arc secant
Yeah.
on yours? Okay,
mine.
which means you're gonna get an absolute value of x up there.
That's
should I
mine.
put that on
So here you would say, okay, let u equal the arc sine of x. What's du?
1 over square root of 1 minus x squared.
Which is right there already.
You should equal dx.
So when you substitute in, ignoring the boundaries for a minute, right, that's a whole nother issue. Then that 2 is just hanging out. Your u is sitting there in the top, and this right there is your du. So essentially, it's the same thing as before.
Du.
U. Du. Okay, so I'm going to take a slightly different approach on this one, Siler.
How's putting in the one with the arctangent?
Yeah.
On the homework, and they got it wrong as 0.
It says it's not 0.
Yeah,
It says it's pi
the
squared over 16,
pi squared over 16. That's what it says.
and the other one says 0 and that. It's okay. Wait, 6 7 precise. The symmetry.
What? Did you have the same boundaries?
Yeah.
So yours is exactly like this one that says it's not 0?
Mm-hmm.
Yeah.
Let me see.
Only difference is that it says symmetric. so it's
1
probably
is
the
7
same.
under 10. No.
The hell? That one is number 11 and this one is number.
Yeah, I had the
It
same
might-
one for both of them.
It might just be a problem with them again.
Yeah, number 10 wasn't taking any visual math, but 16.
That looks identical, right?
Mhm.
Okay. So maybe number 10 has a programmatic error in it. All right, I'll have to investigate that after. I'll make a note. Ruby, make a note.
Yeah, I'm not going to. That's what you said that.
Secretary. No.
Okay, so I'm going to look at this just a slightly different way. If a function is odd symmetric, that means that points are symmetric to each other around the origin. So if I have a point, say, over here, there's going to be a matching point over there, and if you draw a line connecting to those 2 points, it goes through the origin. Okay. In other words, if I have the point over here, x, y, then I also have to have the point -x, -y. And so that's in the first and third quadrant. Same thing goes for the second and fourth quadrant. If you put these together with function notation, then what you get is if you plug in a -x instead of an x, the negative pops out and x remains the same. That's the definition of odd symmetric. Nice thing about odd symmetry is if you integrate through symmetric boundaries of a function that's odd symmetric, you always get 0. Okay? So if f of x is odd, the integral from, say, -a to a of this function has got to be 0. The areas are going to balance out, positive versus negative. Okay. Can you just look at the graph and say, yeah, that looks odd symmetric? Sometimes, but not always. This is the real test right there. Okay. So the function we were looking at just a moment ago was f of x equals twice the arc sine of x over the square root of 1 minus x squared. And the question is, well, what happens here if I plug in a -x instead? I'm just going to rewrite this and then sneak a negative there and sneak a negative there. And then here, I would have a negative x squared like that. Now, this requires some knowledge about the sine and the arc sine. Is the sine an odd symmetric function? Do you remember a trig identity that says the sine of negative x equals the sine of x, or opposite of the sine of x? Yeah. So that's something you just got to remember from trig. The inverse function is also going to be odd symmetric then. So what that means is my numerator, I can pull that negative out, so I get negative 2 times the arc sine of x. What happens if I square negative x? I get just x squared. So the denominator could be rewritten as 1 minus x squared. So the negative I started with on the inside is now popped out to the outside, so yeah, this is odd symmetric.
Well, wait.
I now have the opposite of the function I started with.
Oh, you had f negative x?
I plugged in a negative x, and that negative popped out. That's the definition of odd symmetric.
Oh, okay.
If you can prove that, then you can say, oh yeah, not only does the graph look symmetric, it definitely is symmetrical of the origin. If that's the case, then you can just say, hey, it's odd symmetric, the answer is going to be 0. So there must be an error in problem number 10 in the way it grades it. So that was 11.
That's just it, trash the whole assignment.
Okay,
Okay, this was
that's
problem
right.
number 2240. 10
That one just worked.
is problem number, okay, so it's got a different problem number, 70, yeah, oh, it's a later number, so someone rewrote problem number 11.
Yeah, we wrote it wrong.
And they made a mistake when they, oh, well, this one goes from 0 to 1/2,
I got, so on
which is
11,
not symmetric. How do I get a new version? I just hit submit.
now you can just try it.
Oh, it says, okay, try similar.
That's not
Cotangent, I can't remember if cotangent is odd symmetric or not.
Well, tangent is,
What about cosine? Is cosine also?
because it,
Tangent is,
so wouldn't the inverse function be?
this isn't the inverse of tangent though.
Oh.
Cofunction is different. So for example, sine is odd symmetric,
Oh, no, but
cosine is not odd symmetric.
cotangent still is, because it's just like negative tangent.
Yeah, cotangent is.
It is odd
Yeah,
symmetric?
because it's
Okay.
just like tangent.
No, I put in
backwards.
0 for that one, and they said no. It's not 0.
Does it have to go through the origin to be?
It's
I'm not-
it's arc
It does not have to go through the
It's
origin.
arc cotangent.
Or cotangent, okay.
Oh, so this is arc cotangent. Yeah, I'm not convinced it's odd symmetric.
It's not.
It's not.
I
Okay.
had that one. and I
Yeah,
put
so then I'm gonna get a non-zero answer here, because it's not odd symmetric.
I think
I'll
10's
double check about, there definitely seems to be a version of this that's not coming out right though.
You just.
Just don't be a problem. That's what we're doing.
That button wasn't there a minute ago.
It was-
Cosine is not odd symmetric, so this is gonna be non-negative, non-zero. I'll check it out some more, but I don't think, well, the Seiler's problem definitely looked broken to me.
What about arc secant? I can't.
There it is.
0 to 1/2, this is non-zero because the boundaries aren't symmetric. Yeah, I'll look at it some more, but I want to move on to something else right now. Okay, so I want to go back to the problem from yesterday. So we're going to make a couple Riemann sums. Problem from yesterday was f of x equals x squared plus 1. What I want to do is I want to find the area as x goes from 0 to 2. And first what I want to do is I want to do it with a right endpoints and 4 sublevels. So I want to find what's called R4, which is what I want to find first. And then we'll generalize it. So anytime you do a problem like this, first thing you should do is graph it. So I'm going to make a quick sketch. X squared plus 1. So let's see, it's got a vertex there, and then I need to go over to 2 that way. Let's go over to negative 2 that way. If I square 2, I get 4 plus 1 is 5. So 1, 2, 3, 4, 5. So I have a point about there, another one over there, there. So this is my function. And the area I'm trying to find is this one right in here. Right there. So first thing we're going to do is we're going to chop this up into rectangles. Maybe. And so let's see, from 0 to 2, delta x would be the width, which is 2, divided by the number of rectangles, 4, be 1/2. So every half a unit I want to draw in a rectangle.
Do we have to draw the graph on the test?
Yep.
Okay.
Yeah,
Will you
I'll
give
draw
us a
on the practice
graph on
test. So
the
there's
paper?
my rough rectangles to the best of my artistic ability with this pen at the moment.
So right means you connect it to the right range.
Just grab the right side of each endpoint, yeah.
Which part
So-
of the test is?
So if I blow up the interval, here's 0 over there, there's 2 over there, 1 is in the middle, I need 2 more intervals, so they would be 1/2 and 3/2. So that means for this first rectangle here, that's the x value I'm going to plug in.
You just
So the area of the first rectangle would be plug in that number, 1/2 squared plus 1, and then multiply by the width of the interval, which is what?
1/2.
1/2. Move on to the next interval. Tyler, what's up?
Is this similar to the surprise quiz that you gave us a while ago?
This is just like the surprise quiz I gave a while ago. Yeah. So then the next I would plug in 1. So I have 1 squared plus 1 times 1/2. So right, that was the second interval. So I got that rectangle. Move on, find the next rectangle, plugging in 3/2. So then I'm going to add on to that 3/2 squared plus 1. And, right, so this is height times base each time. Base is my delta x. Last rectangle, what's the height?
2.
Squared plus 1. Width
Uh-huh.
times 1/2. Now, run that in your calculator, get a number. Right, so let's see, I'm going to put that on a new page in a second. So I've got all of those rectangles there. So let's see, 1/2 squared is 1/4 plus 1 would be 5/4 times 1/2 would be what, 5/8? The first rectangle. The second rectangle was what, 2 high times 1/2, so it has an area of 1. Third rectangle, 3/2 squared would be 9/4 plus 1, 13/4. I still count on my fingers, it's okay. Which becomes 13/8. And then the last one, the last endpoint was 2, right? So 2 squared is 4, plus 1 is 5. Half of 5 is 5/2. All right, so you could use decimals if you want here, because those are nice. This is come up with 13, 14, 15, 16, 17, 18/8. Plus 1, plus
28.
2. Oh shit, what happened? That was crazy. 2.5. Let's see, 8 goes into 18 how many times? 2?
Yeah.
And 2/8. Plus 1, plus, sorry, I feel like doing fractions today. It's fun. So that's 1/4 plus 1/2 is 3/4. 5 3/4.
Sounds about right.
Just like that.
5, okay, so 5 3/4, 5.75 if you just plug it into your calculator. So that's an approximation of the area. We want to find the exact area. So now we're going to generalize the Riemann sum. So we're just going to repeat this process without doing arithmetic. Got it? So, next thing we're going to try and find for f of x equals x squared plus 1 on the interval from 0 to 2, we're going to use the definition of a definite interval. That's a question I'm going to ask you on the test. State the definition of the definite interval. So, definite integral here would be from 0 to 2 of x squared plus 1 dx. Now, you all know the shortcut for that now, right?
Yeah.
Yeah, so you're going to do that to double check your answer at the end. But the definition says take the limit as n goes to infinity of the Riemann sum. Riemann sum says you got to plug in some special x value and then multiply by delta x and then add up all those suckers. So we did a sum with 4 parts before, now we're going to do a sum with n parts. We're just going to leave it as n. So first, we'll do this, and then later we'll check with that. To do a Riemann sum, which is that blue thing over there, we just did one a minute ago, right, R4. Step 1 is to figure out what your delta x is. How do I find delta x? Width of the interval. Okay, so 2 minus 0 is 2, divided by the number of rectangles you want. How many do I want here?
And
I want n of them, so it's just 2 over n. That's the width of each rectangle. I want to do a special Riemann sum. I'm going to do a right sum. So that means for my x values, they're called x sub I start at what?
1/2.
Not 1/2. I start at whatever that number is right there. That's supposed to be an arrow, by the way. There we go. So I'm just going to write down, because if that's not 0, you better write down what it is. Don't assume it's 0. So starting at 0, add on
1/2.
delta x. No, delta x, not necessarily a half. 2 over n is your delta x times I.
Yeah.
Okay. So that's always the left endpoint plus delta x times I. That's always the right-hand endpoint. Always look like that.
Okay.
Sometimes it simplifies very nice. So in this case, it simplifies to 2I over n. 2.
That's what determines the x.
This is the right-hand endpoint at every interval. Right-hand x value. So for example, back here, that right there is x1. This right here is x2. This one right here is x3. That one right there is x4. You got to plug those into the function next.
Okay.
Okay. So next, we got to plug these guys into our sum. So again, we're trying to find the sum as I goes from 1 to n of f of xi times delta x. What's our delta x here?
2I over n.
2 over n. It's just 2 over n. Delta x is just 2 over n. Okay. What's our function here?
X squared plus 1.
So we're going to write it as parentheses squared plus 1. So here's the height of my rectangle. Here's the width of each rectangle. Okay, what x value do I get to plug in there?
2i over
2I over n is what we just calculated. Okay, and then we got to add up all these things. Nope, it's the only way to do it.
Are you sure?
All right, we're halfway done. Now on the test, I'm going to ask you to do this in stages. Tell me what delta x is. Excellent, there's 3 points. Tell me what x is. Oh, here's another 3 points. Tell me how to write the sum. 3 more points. Right?
Do we get points for writing our name?
Not today.
Ah,
Well, the test is on Monday, so.
Yeah, maybe Monday. All right, so now we got to try and clean this up. What's the variable in the sum?
I.
I. Keep that in mind. I is the variable of the sum. Come on, here we go. I is my variable. It only occurs once. Everything else is a constant. Okay, so I can clean this up a little bit. For example, this is a multiple of 2n. N is a constant here. I can pull it out of the sum. That's where I start. Find any constant you can pull out. So we're going to pull out the 2 over n. Now, because I'm lazy, I'm just going to write sigma. I'm not going to write the I goes from 1 to n every time. That's okay. Okay, so what's left inside the sum? What's left is 2i over n squared plus 1.
Separate them.
I can, next thing, big thing, yeah, I can separate on the sum. So I'm going to break this into two sums. So the 2 over n sticks around outside. Now I have the sum of the 2i over n squareds plus the sum of a bunch of 1s. Now, I guess I'm going to put the i's back in just to remind you of a special formula. How many 1s am I adding up there?
N.
N of them, right? So if I add up 1 n times, I get
N.
n. Yeah, so this one's a beauty to evaluate. That right there is just n. Now, I'm going to give you some shortcut formulas on the practice test. So,
Test?
the real test, yeah.
Yeah.
The real test. Where the heck is it? What happened to my screen? Yeah.
You pulled it?
I must have closed it accidentally. All right, new one. Math, calculus, practice test. Is that it? Yeah, that's it. So I'm going to give you these formulas right here.
Just those three?
Just those three.
Because we should only need those three.
That's the theory. Yeah. All right. So what do we have left to deal with? An I, an I squared, or an I cubed?
I
We have an I squared. So we're going to need this formula right here in a minute. Okay? But we don't have just an I squared. We've got to whittle it down to just an I squared. So let's do that next. All right. We have a 2i over n squared.
Can we take out the
It's the same thing too.
So we can clean that up. Okay. So here's where we're at now. We have lost my pen. Come on. Come back to me. Come on. There you go. Okay. So we have the 2 over n sitting on the outside. We got to clean that sum up, and now we have a plus n here. All right. So let's see. If I square this thing right here, then I can rewrite that as 4i squared over n squared.
You can pull.
Is 4 a constant?
Yes.
Is n squared a constant?
Yes. Yep.
Yeah, so they pop out. Okay, so now, here's what I have. 4 pops out, n squared pops out. So now I'm just summing up a bunch of I squares as I goes from 1 to n.
No.
It's stuck where it is at the moment. Yeah. So we know a formula for that. It's n times n plus 1 times 2n plus 1 over 6. Put everything else back in. 4 over n squared, 2 over n plus n. Yes, this is a lot of work. I know. A little bit cancels though, nice here. So for example, this n cancels with one of those. 2 goes into 4 twice and 6 3 times. And I guess I need to distribute that in. Okay, so what do we get? We get, there's going to be an n squared at the bottom and a 3. A new page. There's going to be a 4 on the top. There's going to be an n plus 1 in the top, and there's going to be a 2n plus 1 if I am not mistaken. And there's going to be a 3n squared in the bottom. Then I'm going to have 2 over n times n, just 2. So what this tells me is that if you want a right-hand sum for any number of rectangles, this is the shortcut formula. So we could double check by plugging in 4 to see if it gave us the previous answer. That's not what I want to do next. You guys can do that later if you want.
When we get to 2 again?
If I take 2 over n times n, the n's will cancel. That'll be 2n over n,
Oh,
which
I
is
see.
2.
Distributed.
Could you get rid of the one? I mean, like, can you okay, can you just integrate from x squared and add this rectangle n in the integration? Right, because it's a constant slopey squared. So integrate from x squared.
Yes.
And add that one after.
You could use a little geometry and a little calculus mixed together. Yeah. All right, so we found the simplified Riemann sum. The sum is gone, right? It just depends on n. Next step, we're going to finally take the limit as n goes to infinity of our Riemann sum, which is that thing up there.
Wait, how'd you get that 2 on these again?
That came from taking 2 over n times n,
There's 2n.
because I have to distribute this 2
Oh,
over n
okay,
through
yeah,
the whole thing.
I got you.
That's okay. Okay, so now think back to your limit laws. Let's do the easy part first. Is there any n attached to that last 2?
No.
So if n goes to infinity, it's just 2. That's kind of nice. This right here is a polynomial. If you start multiplying that out, it's going to look like 4 times 2 is 8, n squared plus a bunch of stuff. So basically I have a quadratic divided by a quadratic. As n goes to infinity, what's the behavior?
Leading coefficient.
The leading coefficient, yeah. So the limit is going to be 8/3 because they have the same highest power. Yeah, so that one has a limit of 8/3.
Yeah.
Okay, 8/3 is what? It's 2 and 2/3.
Yeah.
2 and 2/3 plus 2,
2.666.
4 and 2/3. Okay, so that's what we think the actual area is in there.
Could have just taken the answer.
Now, you could have, but I wanted to do this too. So we're going to check that that's true by going back to the definition. Remember, our definition said that the definite integral from 0 to 2 of x squared plus 1 dx is supposed to be equal to that limit of the sum. N goes to infinity. I goes from 1 to n of our f of x dx. So we did this. We came out with 4 and 2/3. Now let's do this and see if it matches. Antiderivative.
2x.
No, 1/3 x cubed.
And so we definitely have an x cubed. Divide by 3 or multiply by 1/3.
Plus x.
Plus x. Evaluate that from 0 to 2. So substitute the top one in first. That's going to give me 8/3 plus 2 minus, plug in 0.
No.
That's just a bunch of zeros. What's 8/3 plus 2?
4 and 2/3.
4 and 2/3, same things we found before. Okay. So worst case scenario is you're going to skip all that stuff in the middle and do that. Skip, skip, skip. I hope you don't skip it for real. And do the 4 intervals. So there's going to be a problem like this on the test where I give you a function and then I say follow the steps. Do a Riemann sum 4 subintervals. Okay, now let's switch to n. Tell me what delta x and x sub I are. State the sum. Try to clean up the sum and then try to take the limit. Then use any means you can to find the area another way to see if they match. Okay. That's probably the hardest problem on the test. All right, everyone take a deep breath. What other problem should we do? How about, let's take a look at 31 here. That's a cute one. First, come up with a graph of x cubed minus 2x squared minus x plus 2.
It's just negative x. You can factor it.
It does factor. That is true. Let's try that. Let me get a new page. Get to the end of this stuff. New page. Yeah. So if you haven't already, whip out your graphing thing, but I want to try to do it without. So let's see, this factors as, I can pull out an x squared from the first two, which leads me x minus 2. From the next two, I'm going to pull out a -1. That's going to leave me an x minus 2. So this factors as x squared minus 1 times x minus 2. X squared minus 1 factors, right? So that's x minus 1 times x plus 1 times x minus 2. So graphing this thing, I have zeros at 1 and -1 and 2. Since it's a positive x cubed, it's got to go up on that side and down on that side. So it's got to have humps in between. Something like that. Question is, how high are those humps? And I can see what? This hump is at least 2 high because 2 is the y-intercept. It's probably higher than that, actually, because I don't think 2 is where that happened, or 0 is where that happens. I'm not positive. So, and I asked, let's see, what was the question here? Integrate from -1 to 2?
If x is 0, it has to be 2, so y has to be 2, so it does have to hit.
It does have to hit there, but that's not necessarily the max. Yeah, I don't think that's the max. It's not, yeah, I didn't think so. Cubics aren't symmetric like parabolas. Where's the problem? Integrate from -1 to 3. Okay, I got to go even farther. So if I were to plug in 3 here, what's the y value? 4 times 2 is 8. All right. So this goes all the way up to 8. So there's going to be a point up here. That's the point 3, 8, I believe. So what happens when I integrate this is I'm going to get some negative area here. And I'm going to get some positive areas here and there. So if I just do a straight integration, is some stuff going to cancel? Answer, yes, some stuff is going to cancel, right? Whatever's here is going to cancel with some of that positive stuff right there. So whenever you just integrate and you don't worry about positives and negative areas, is that called net area or total area? Net, yeah. This right here, if you just integrate without thinking about positive and negative areas, that's called net area. Really, I love net area. I just integrate. It's a mindless process. Find an area, plug in the numbers. Don't think about it. If I ask you to find total area, which I do here, last problem, then that means you have to find every place the function changes sign and integrate them separately. So you would have to integrate from -1 to 1 separately, from 1 to 2 separately, from 2 to 3. So that's going to have to be broken into 3.
And that's the difference between like
Total area
displacement.
Displacement and total distance. Yeah, displacement is net area.
Okay.
Total distance is total area.
Okay.
Yeah, William?
Net area, isn't it like between -1 to 1 and 2 to 3 in the net area?
That would be total area. Integrating separately each region is total. And then you would have to take the opposite of this because that's a negative area there. Okay? So keep in mind, there's going to be at least one question on the test where I say, hey, integrate, give me the net area. Integrate again, give me the total area. Which means you got to analyze the functions, find the place it switches from positive to negative, and break those up and do separate integrals. All right, so we're out of time for fun today. William, question?
What's the net area?
The net area would be just a straight integral from -1 to 3. And you don't have to, stuff will automatically cancel for you. You don't even have to worry about it.
Total area would go for your.
Total area would be this plus the opposite of that plus that. You have to do them separately. Yeah. Okay, so
much-
tomorrow, does anyone want to take the test tomorrow? You have to take it by Monday.
If we,
By Monday,
So do you want to take it tomorrow?
when we
Who else,
take,
you want to take it tomorrow?
By Monday at what time?
No?
when we take it, how much time do we need to reserve for the fun?
You have an hour to take the test.
Okay.
You have an hour to take the
I
test.
don't
Hey, you
need
say
hours
that,
on
I
it.
go over every time.
So, I'll cut you off next time.
That's okay.
So, my preference is you take the test at the usual time class meets. If that's not the case, then you need to let me know when you think you take it and skip on the board.
Can you take out my transcript really quick? My grade. So I can put that in.
So, those of you who aren't gonna take the test tomorrow, I'm gonna put the testers in the other room and we're gonna review in here. So we're just gonna do more problems, whatever you guys wanna do, okay? All right. Take care, get some rest, do some math.